Assalamu alaikum. Hope you are doing fine. We know when two charges are brought close to each other, they experience a force. Similarly, a force exists between two magnets. In this video, we are going to discuss about a force that acts on a moving charged particle in a magnetic field. For that, I consider a coordinate system, which appears something like this. Here, the coordinate system has got three axes: x-axis, y-axis and a z-axis, acting mutually perpendicular to each other. Here I have used the term mutually perpendicular. What does it mean? Mutual means between two. Here if you take any two axes, you will find that the angle between them is nothing but 90 degree. Here y and z is perpendicular to each other. The angle between them is 90 degree. Similarly, x and y are perpendicular to each other. The angle between them is 90 degree. Again, if you check the angle between x and z, it is also 90 degree. But it is not obvious from the diagram. Only the angle between y and z appears to be 90 degree. But the angle between x, y and x, z do not appear 90 degree from this diagram. The reason is actually the coordinate system appears something like this. Let me show this to you with the help of this three chalk piece. I take this one as x-axis, this one as z-axis. The angle between them is 90 degree. Then x-axis will be projecting in this manner, projecting outward. Here on a blackboard we cannot draw a line which is projecting outward. So in the place of that line we draw an inclined line. Clear? Now look at here. The angle between the x-axis and the z-axis is 90 degree. Again, the angle between the x-axis and the y-axis is 90 degree. So these three axes are mutually perpendicular to each other. I hope you have understood. Now, in one such coordinate system, if I take a particle with a charge plus q moving along yz plane, now these two axes combine together to give a plane. These two combine to give us a surface. We call that surface as plane. Now I say that plus q charge, a particle with plus q charge is moving along yz plane with velocity v in this direction, making an angle theta with the z-axis. Okay? And here, I forgot to mention, the magnetic field, uniform magnetic field is considered to be acting along z-axis. Then along y-axis we have a Vb sin theta. What is this? We will come to know that later. Then here as plus q charge moves with velocity v along yz plane in a uniform magnetic field B vector, a force acts on the charged particle, and the direction of that force will be acting along the x-axis in this way. This is the force acting along the x-axis. Clear? Here, this force was studied by H.A. Lorentz. So it is known as Lorentz force. It is also known as magnetic force, which otherwise known as magnetic Lorentz force. Okay, it is named after a scientist to honor him. Clear? Now, how we can represent this force mathematically? Let me show this to you. The magnetic Lorentz force F vector is mathematically represented as Q into V vector cross B vector. This is the expression that represents the Lorentz force. Clear? We know, what do we know? We know that the cross product of two vectors. If I have A vector cross B vector, then it can be expanded as AB sin theta. Clear? If I use this relation here, so what I get? I get this. Here I have V vector cross B vector. Here V is the velocity with which the charged particle is moving, and B is the magnetic field. Clear? Then this comes to us VB sin theta. This I am going to use here. This is the expression. So what I get this. F is equal to Q V B sin theta. Q V B sin theta. This can be rearranged and written in this manner. The manner of F plus B Q V sin theta. For our convenience, it is represented in this manner. Now I box this expression. Yeah. Now, H.A. Lorentz have formulated the special features of this magnetic force, which are as follows. So let me give the title: Special Features of a Lorentz force. Lorentz force is that, you see, the first feature is the force acting on a charged particle will be zero when the charged particle is at rest. When Q, the charged particle, is at rest. You remember this. If the charged particle is at rest, no force will be acting on it. This clearly shows that the Lorentz force acts only on the particles, on the charged particles which move in a magnetic field. If we have a charged particle placed in magnetic field which is at rest, then the Lorentz force acting on that one will be zero. Remember this. Similarly, if the charged particle moves, parallel to the magnetic field, then the force will be zero. Then F will be equal to 0. Okay. What does it mean? Let me show this to the help of a simple diagram. Here, I consider this one as the direction of magnetic field. The magnetic field acts in this direction. Then the charged particle also move the same direction parallel to it, then in such case force will be 0. No, Lorentz force will be equal to 0. Yeah, in a similar way, say force acting on the charged particle will be 0 when the charged particle moves anti-parallel, moves in direction anti-parallel to the magnetic field. Magnetic field. What does it mean? Let me show this to you. The help of diagram. See, this is the magnetic field. If the charge moves parallel but in the opposite direction, then we call it as anti-parallel. In such case, Lorentz force will be equal to 0. Where the Lorentz force is 0. Clear? So for these three cases, when the particles at rest are moving parallel or anti-parallel to the magnetic field, in these three cases, the force acting on the charged particle is 0. Clear? Then the remaining features can be obtained very easily with the help of this expression. Okay, let's see. The force, the Lorentz force acting on the charged particle will be directly proportional to the magnitude of charge. Clear? Then, see, as the value of a charge increases, the force will also increase. Suppose if I have a 10 Coulomb charge, the force acting on the charge will be something. Suppose it is a 10 Newton. If we take a 20 Coulomb charge, then the force will increase. It may be 20 Newton. Clear? So it increases with increase in the magnitude of charge. The next thing, the force, the Coulomb's force, the Lorentz force acting on the charged particle is directly proportional to the magnitude of magnetic field. No? If I increase the value of magnetic field, the force acting on the charged particle will also increase. Clear? Next, from this, what do you understand? Here, this is said F is directly proportional to B, F is directly proportional to Q. And from here, the force, Lorentz force, is also found to be directly proportional to the velocity with which the charged particle is moving. Clear? F is directly proportional to V. Remember this. Okay? And one more thing is there. It is also, the force is also directly proportional to the sine of angle theta. Here theta is the angle between V and B, velocity of the particle and the magnetic field. Clear? I hope you have understood. The next step, from this expression, we are going to get one thing. As V and B are in a cross product in this expression, so F is found to be perpendicular. It is a perpendicular. Perpendicular means acting at 90-degree angle. Perpendicular to V and B. The direction of V and dV. Here, force acts perpendicular to velocity and magnetic field. Yeah. The next, what if I have a negative charge in the place of this in a uniform magnetic field? Okay, let's find out that. For that, I take this another coordinate system. This is the x-axis, y-axis, this is the z-axis. Okay. Here, magnetic field acts along the z-axis, and in the place of positive charge, we have a negative charge here. Let's see. Take a negative charge, and suppose it moves in this direction with velocity v. Then the magnetic Lorentz force will be acting in this direction. Okay, this is the direction of a magnetic Lorentz force. It acts towards the origin. Whereas here, in case of positive charge, the force acts away from the origin. Okay, so we can say the direction of force is in the opposite direction. Okay, let me write this properly. The direction of force acting on the negative charge. The direction of force acting on negative charge is opposite to that of plus Q charge. Clear? See, for a positive charge, force acts in this direction. For negative charge, force acts in the opposite direction. Clear? So these are the features of Lorentz force. Now let me tell you what happens when the electric field acts along with the magnetic field on a moving a charged particle. In such case, the force experienced by the charged particle due to electric field is, say, I take it as Fe. Fe is the force acting on the charged particle due to electric field is a E vector dot Q. No? Then the magnetic Lorentz force is this. I take the magnetic Lorentz force as Fb vector. Here I am discussing about the case in which both electric field and the magnetic field is present, in which a charged particle moves with velocity v. So that the force experienced by the charged particle is given by this equation. Then the force experienced by the same charged particle is given by this equation, v vector plus b vector. Yeah. Now the total force acting on the charged particle is obtained by adding these two. Now if I add this to F E vector and F B vector, I get a total force. I represent total force by letter F vector. Okay. So I am going to substitute this 2 in this equation. I get this. F vector equals to E vector dot Q plus Q into V vector cross B vector. Okay, this can be written in this manner. How can I write this? Simple as F vector equals to, then in both the cases Q is common, so I take it out. Then get E vector plus V vector cross B vector. This is the total force acting on the moving charged particle in the presence of electric field and a magnetic field. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.